I'd like to thank everyone for this opportunity to present some work done by one of our PhD students who actually recently graduated. And I also would like to thank some of you who've been part of the examination committee. A very warm thank you for all of them, because I know how difficult it is to read the thesis and do all the rest at the same time. Nowadays. So the motivation for this work actually came out from some of the cruises that have been that South Africa has been doing, taking advantage of a window of opportunity during winter time that allowed us to go down a few times, particularly in periods when previous measurements of MIZ conditions have not been taken. And this is a combination of some of the knowledge we put together. And as part of the very good document that this team put together, I also would like to bring in some concepts related to the rheology. And I'll give you a few perspectives on what we've been the leading on this one, and some others who are also online here have been part of the team doing this one. It's published on the Cryosphere if you want to know more about that, but I'll be putting together a few more information from other works and other ongoing activities that we're doing at the moment here in South Africa as part of the Marine and Antarctic Research Center for Innovation and Sustainability. So part of this has been also sponsored by Crisis, that is a European project, and Scale that you see up there is the name of the experiment we've been running for a few years. So we basically started in 2017 with an expedition in winter. It was a very short expedition that allowed us to deploy a few buoys, the same ones actually used by Alison Cohout. And then in 2019, we had some more cruises in winter and spring. And then I would like to bring in some comparison and interesting outcomes and differences and contrast, which is the title of this one, with the Piper's buoys deployment that were done in early winter 2017. So without much, let me go to the next. So the origin of all of this is another work that we've been kind of lucky to deploy a buoy in 2017 that actually has been spinning around in the marginal ice zone and without ever leaving the marginal ice zone for approximately 4 months, and running from, as you can see on the right hand side on the top, running from approximately 30 east to 56, pretty much until the very end. So what you're seeing here is the sea ice concentration at the time of when we lost track. So this is ice tethered buoy, which was meant to sink when sea ice was melting. And what we learned from this experience was that we definitely saw very much, particularly the relationship between polar cyclones and the way they affected the drift. Nothing new. This has already been measured previously, but this time with the certainty that everything was on ice, we could actually start learning something interesting. So we could see that the increased meandering and drift speed, changes in dispersion regimes, all of them were related to the presence of cyclones. And we also could see a very clear, as you're seeing from the spectrum on the lower right side, and this is for the meridional wind and sea ice drift in blue. You see this very clear peak at approximately 13 hours, which is the inertial signature that has been running around throughout the entire period, not only at the beginning, but also during the evolution into spring and into summer. So the last day we could retrieve data was the beginning of December. So it's been a rather long journey for this buoy. The dominant atmospheric control went on for long, and all the time sea ice was more than 80% covered. We were 200 kilometers from the ice edge, so there were clear, persistent, free drift conditions that told us quite a lot about the rheology of all of this. And then we thought, well, we're starting to learn something, and we were very keen to compare with other data we got from other deployments. Now, we've been testing different buoys in this case. These ones, they were commercial ISVPs from mid-ocean, very expensive ones. They were not ice tethered in this case, so actually they left at one point. We didn't really know what was going on, and one conclusion of the paper from Ashley is that actually they are not the best for following Antarctic sea ice drift in the marginal ice zone. But what we found was a clear response to wind forcing for the first few days. You can see from in the bottom part, we've been using the trajectory stretching exponent, which is another measure of dispersion and stretch and Lagrangian coherent, and identifying Lagrangian coherent structure proposed by Holler and then Aksamit, who developed it particularly for ice applications. You can see significant stretching and compression, which is very good. This indicator is giving you positive and negative, so you can separate the two components. And you see that in the passage of cyclones, identified looking at the lower left panel, identified by the yellow stars, you can see that you have a much larger stretching and compression all the times the cyclones are running through. And another thing we noticed, and you can see from the trajectory on the upper side, that there was a clear effect of the Antarctic circumpolar current. On the left-hand side, you see a reconstruction from NOAA of the fronts of the Antarctic circumpolar current throughout the year. Actually, it doesn't change much. In the yellow circle you see there is where we've been, is the region of deployments, the region of the trajectories, and you can clearly see that it was pretty much along one of the major fronts. And you can see this by looking at the again at the spectral density that you see on the upper right. This particular case, you see the wind, the ERA 5 zonal and meridional that are on top, the first two lines on top. And as you see in the zonal and meridional drift velocity from the sea ice, here we removed those who we are pretty sure they were in the water, according to the meandering coefficients and other information. We can't exclude entirely that some of the other buoys were always on ice, but that is very difficult. This is why we are a bit confused in here. But you can see this flattening of the spectrum at higher frequencies, which is not following what we used to be seeing in all our other winter expeditions. So this is indicative of a presence of energy at higher frequencies that we explained as part of the Antarctic circumpolar current that has been driving with non-linear mesoscale signals the drift of the ice. So not only atmosphere in this particular case, so a clear contrast. And another clear contrast was the entire absence, and if you look at the wavelet power spectrum at the bottom, is the complete absence of inertial oscillations. Nothing. So all energy is approximately at 4 to 5 days, which is the scales of cyclones passing by. And there's a lot of energy at the longer scale, which we also attribute to the Antarctic circumpolar current. So here we are seeing that the location of our measurements and the fact that this one is a location from the zero meridian moving westward, moving eastward all along the Antarctic circumpolar current is dominating the reconstruction, how the sea ice is responding to all the different drivers. We've also been looking at the deformation rate, particularly the standard deviation of the deformation rate, which is a proxy for strain rates. And we did see some pronounced fluctuation. This is the plot on the right related to the currents of cyclones, even if it's not that clear because you can't do a clear correlation onto this one. You go from higher deformation to lower deformation conditions and so on. If we look at the spectra, now this is the spectra of the deformation rate. This is still showing this interesting decay. Majority power found at the same frequencies of large-scale atmospheric forcings, and it's different from, if you compare with the previous one, from what we're seeing from the drift. So the rheology is kind of responding more to the atmospheric solicitation and somehow kind of the baseline from the Antarctic circumpolar current. Now let's move to spring conditions, same years. pretty much same type of, now we use the mixed type of buoys. In this case, we use the surface velocity profilers, and one of the older buoys that we used in 2017, and the combination of all of them. So we've been testing a few things, and I'll show you where we're moving it now. So what we found, so this is now the deployment from the 24th of October, and then it lasts for approximately a couple of months, and you can see the trajectories of the 4 buoys we deployed on the upper figure. You can see a very interesting trajectory in that particular case. But if you look at the trajectory stretching exponent, you see that at the beginning, approximately until the beginning of December, besides these cases of very strong stretching occurring kind of beginning of November, possibly with the passage of a cyclone, again, the stars on top are indicative of those ones, you can see that there wasn't much stretching. So here the rheology is at play. So the sea ice stresses, internal stresses are working. And if we go back to very quickly to give you an idea what was the conditions, this is in the upper side, this is the condition of the deployment, and you can see one of our surface velocity profilers, which we constructed this particular cage to ensure that it was staying on ice as much as possible until full melting. So in the spring condition, after a while, we start seeing from November on, and in this particular case, it is because of the atmospheric conditions. So there is air temperature began to increase approximately kind of beginning of November, causing sea ice cover to melt and break up. And you are starting to see the compression and stretching increasing in the TSE, as well as the propagation of waves. This case, just to remind you that the location of deployment is indicated by the yellow circle on the lower left animation that is showing the front. So we are south of the front in this case. And this is another example of deploy. Oh, actually, I had it much closer, these figures. I didn't have to go back. You can see at the deployment, and you can see some other images all along while we've been in ice. And some of these images are also coming from, this is, all our observation. You can see how the sea ice has been fracturing and coming back. And at the same time, we deployed some swift buoys from Jim Thompson. That kindly made them available to us. And if you just look at the green thin line on top, which is showing the significant wave height, you can see that from the beginning of November, there is a clear presence of waves, 1.5 meters significant wave height. This is the Swift number 20, the light green. And it's clearly indicative that from November on, more waves propagation have been coming in. So due to the progression towards the free drift condition, sea ice became dominated by the initiation of inertial oscillations. And this is interesting because now we're going into spring and we're starting to see the inertial oscillations coming back again. And in the wavelet power spectrum, you see that right after this November period, and there is also correspondence with some polar cyclones, but you can't distinguish the two things because temperature has been increasing substantially over that time due to the seasonality. And we do see a much clear signal of the inertial oscillations. You see in the spectral density plot on the top right, but it's got a different shape from the winter one. There was a single specific peak. This one is a lot more extended with more energy.
To the toilet, take your shoes off.
Into the higher frequencies. And then the overall drift exhibited majority power around this inertial frequency, which is somehow indicative of the geostrophic current not dominating all of this. So the Coriolis component was very much the driver. There was an increased mobility of ice flows because of the wave penetration, and then additional ingredients are coming in to complicate all of that. So I'm pretty much sure that you would like to see some solution of all of this. I'm not sure I'll get to that, but I'll do my best. Let's look at the deformation. If we now do the same analysis of strain rate, which is again taken by the standard deviation of the deformation rate, that was pretty constant. These are two buoys on the top right with the light pink and the purple color. They have two different time scales, because we had different scales. The buoys were separated by different initial scales, 100 to 200 kilometers, 300 to 600 kilometers. And what we're seeing clearly, deformations higher when you have smaller scales, and deformation lower at larger scale, which is what the Rampal has already been showing in the Arctic. And this it's confirmed in the marginal ice zone as well. But what is interesting here is now the spectral analysis of sea ice deformation. No energy cascade at all. The power at the lower frequency has been dampened out, and there is a strong decoupling between the large-scale atmospheric forcing that's got exactly the same decay that we would expect, and the deformation. So it's flat. We got energies at all scales in this particular case. So the sea ice melt is known to produce an outer kind of sub-mesoscale eddies. There have been a few measurements done by Göteborg people, and that's what we're seeing. There is some sort of underlying ocean energy that is contributing to this energy in the deformation component. Let's try to put everything together. This is the family picture. What we've been learning, and actually not much, but at least we have some idea. There are very few measurements like this ones in the marginal ice zone. And here we are combining together all the kind of winter type measurements, Indian Ocean in winter 2017, Pipers in the Ross Sea in early winter 2017, our 2019 winter, and then the spring. The spring is the longest one, and unfortunately the duration of these ones depends on the number of buoys that are available for doing this analysis. If you just focus on this initial time for the 10-day scales, there's everything going on. So at 1 kilometer scale, because in this experiment 2017 we deployed very close, of course we are seeing the highest deformation, and then as we go to the bigger, larger scale, the deformation decreases. So deformation is scale dependent. However, if we now look at similar scales, like the red for 30 kilometers, sorry, not this one, the red for 30 kilometers, the light blue, and then you go again into this one and at the green here, then we also see quite a lot of difference. It's 3 orders of magnitude changes in the deformation rate. All pancake conditions expected to have similar ice rheology, but they don't. So wave conditions are definitely impacting the rheology in this case. So what we can conclude is, of course, the obvious, but this obvious is also percolating into our estimation of rheology and how the sea ice and the stress component and the momentum transfer would be modifying the underlying ocean. There's a strong interplay between all of this, and data scarcity is our most limiting factor into here. That means we need to start improving all of this. These are the buoys we're using at the moment, built using off-the-shelf components. They are a fraction of the cost of the mid-ocean, because we really would like to deploy at large numbers to start seeing a majority of the multiple various scales. This is an example of the deployment. We deployed in these conditions, and 4 days later, this is where we've been retrieving. This particular case was a deployment and retrieval experiment, because we had onboard storage of very high frequency information. In some cases, actually, this one was found, one of our buoys was actually floating because it sank down. There was, you can see, in 4 days, sea ice went from that condition to this one in 2022. We were already going into this particular new regime that we are going on at the moment. These are the data. If you're interested in some more, they are published on IEEE in a symposium, and you can clearly see that there are these are acceleration at 104 Hertz in heave axis from some of our buoys. These are recorded over 15 or 30 minutes, and this is just a portion of that. And you can clearly see these spikes that are attributed to flow collisions. So collisions don't happen continuously. They just happen at one portion of the stress exerted by the wave, which is somehow helping us to understand a bit more the initial ideas of how the marginal ice zone is being shaped. And with this one, I thank you very much. My 20 minutes, guys.
Fantastic. That was a very, very nice talk to start with. We have a few minutes for questions.
Maybe I can chime in here. Yeah. Also, it was an awesome talk. I mean, there's an enormous amount there. It's hard to take it all in, and it's fantastic that you're making all these measurements as well. And you know, we all know how difficult they are to make. But it just that final slide with the collision there just really fascinates me, because you can see that those collisions are occurring clearly periodically with the wave. So, and it's, I just, so many questions, but I wonder how much you could extract out of that, try to integrate and get a sense of the force, etc., because it's probably quite hard to calculate that, is it or not?
Yes, it is indeed. We would need two closer buoys to start learning a bit more about that. The high frequency is essential. I mean, we've been pushing for this from the beginning, because when you buy commercial buoys with accelerometer, they have already decided, I mean, Jim Thompson has already explained all of this, so what type of acceleration, what type of waves you are retrieving. So we know very little about the conditions and whether the waves are effectively impacting on whether the accelerometer are exactly measuring the wave or any other combination of the forces that are going on. I'm not sure we will get there. It's very interesting that all of this is only happening in the trough of the wave. So this is, it can't be separated from the environmental conditions when this happened. So our problem is that this, well, we know what was happening, that was melting slowly, there was breaking, and then the waves were coming on into our system. So we can probably start learning a bit more about all of this, especially in light of what Rutger will be showing now, which is our attempt to do the modeling of all of this. But I'm not sure we can get there, but hopefully these are the data, and anyone who's got idea, I mean, we're very happy to share this data.
Got a few more questions, but maybe someone else has another question. Because one of the issues is with this whole project is sending the data back. It's very expensive, but is that changed now? Is it possible to, because a lot of these original buoys were doing all this processing on board, so we never had the raw data. We only had it for a few hours. There's all kinds of, so that really limited the. So
yeah, that was the reason for designing them, because you can have bursts of data at very high frequency being sent while the onboard processing is still calculating the parameters, the wave parameters that we want to have. But every now and then you can send a burst for 5-10 minutes. It's going to be very expensive unless Starlink is coming to help us a bit, hoping to send a bit more data. In that case, for us, it was, I mean, sending anything through the current networks is just impossible. That's why we prefer to have this experiment of staying 4 days. Then we went out when the storms was coming, and we got back.
Okay.
Collected.
Yeah. I mean,
it's expensive because you have a ship in that case.
Correct. Yeah, I'm wondering, it seems a bit strange to me that 4 days of ship time is less than a Starlink receiver, but I don't know, the economics of
no, well, now we know.
For the ship.
Now we know. I mean, we had to do it once because there was no other way to demonstrate that it was working, because none of the commercial systems allow you to do that. You need to do it on your own. There's no other way. Luckily enough, we got great MSc students like the ones you see on the right here that have been able to design these embedded systems and make it work.
How see if someone else wants to ask a question, otherwise I'll ask. But you're just another thought, you feel like deploying them on the ice. It always seemed like a bit of a cop out that it'd be better if they floated and all that. But you actually think that's a good idea to have them so that on the ice.
We're very much convinced about that one. You'll never be able to separate. I mean, because of the nature, the heterogeneous nature, you will never know whether you are in the interstitial ice or not. As you can see, look at Look at how quick
But
in
isn't
4
there an
days.
issue? I'm always worried that you're measuring a bit of ice moving, not the water moving. There's this other kind of, but
Well, which is what we actually would like to do. I mean, part of our experiment, we also been testing what is the response of a solid body when you have the motion of the ice on top of this. I mean, I don't know if you can see the stand is quite tall,
yeah.
because sometimes the snow could become a problem in certain cases. We have been running some other computational fluid dynamics experiments to see what is the rigid body response of a flow with this one on top, because we really want to know what we're measuring and how much of that is related to the underlying waves. What I can tell you is that clearly we're not measuring the waves now. We are measuring the effect of the waves on the ice, which is pretty much what I think is essential for numerical models to calculate the rheology and the stress and internal stress for the sea ice. I mean, a combination of both is probably what we need.
Yep.
Just an obvious point. Surely, if you put the buoy in the water, the flows would destroy it very, very quickly.
Yeah, that is true. You see, we are trying to collect too many information, probably too many information at the same time. How long the flow is in the air, and at the same time some other environmental information. So I think the solution would be to have one ice tethered buoy and then one buoy in the water, which in some cases it could also freeze, and then you will never know what's actually happening, because the interstitial ice, the thermodynamics of the interstitial ice is something we actually don't really know. 15 days in winter conditions will get you through such a variety of different ice types that we are just scratching the surface, because we've been there so few times. And this is one region of the world. I have no idea whether East Antarctica does develop similar things. This is pretty much the problem. The data paucity is just limiting our knowledge here.